Okay. So I want you guys to relate these four factors that affect the rate of a reaction to the collision theory. So the collision theory has those three parts, and what's the first factor that affects the rate of a reaction? It's state. Okay, so the state of the substance matters. So I've got state, and state equates to what? If they're in a liquid state or an aqueous state or a gaseous state, they're more likely to run into each other than if they're in a solid state. Plain and simple. I can't hit, the things inside of a solid can't hit each other. Only the surfaces can. And the next thing? Concentration. And that has to do with collision. I got more of them, they're more likely to run into each other. And there isn't anything else to it. The brackets, what's that mean? More specific. It means moles per liter. What's the third thing? So if I increase the temperature, then when they run into each other, they have enough energy to actually break their own bonds and so they can form new bonds. Since we're talking about chemical reactions, we're combining, separating, and rearranging those atoms. And so I need to break some stuff. And then the last one? And that has to do with orientation. The catalyst takes the molecules and orients them in a way that they're more likely to run into each other in the correct orientation. All right. And a catalyst. For something to be a catalyst, what has to happen? Yep. It's got to increase the reaction rate, and itself has to be not used up. 62 degrees Fahrenheit, delta S, delta H, blah, 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 spontaneous reaction. Okay, so 62 degrees, first thing I'm going to have to do with that is minus 32, and then multiply by 5/9. Does anybody have a number for that? What? $16.7982 degrees Celsius. Does that number make sense? Does 16.7 make sense for the degrees Celsius for 62 degrees Fahrenheit? Why? What can you relate it to? Which is about 20-ish, low 20s, high teens for room temp. Okay, so that number makes sense. Now I'm gonna take this number right here and make it negative 2200 joules per mole. So my numbers, my units can be the same. And so my delta G is going to be equal to negative 2200 joules per mole minus 289.7 K, and then I had 9 joules per mole K. K cancels. And so I've got negative 2200. $289.7 times 9. Negative 4888 joules per mole. And looks like I got 1 sig fig, so -5 kilojoules per mole. And is this reaction spontaneous? Did we know that before you did the math? You did, because it lost energy and it gained disorder. So we knew it was going to be spontaneous before we did the math. All right, what is the order of reactants for each of the reactants in this trial? Okay, so I've got trials 1, 2, and 3, and so what I want is A with an exponent and B with an exponent. So what are those exponents? How are we going to figure that out? What's your process? Trial 1, what about it?
It doubles an initial A and also doubles a weight.
You mean 1 and 2, trials 1 and 2?
Yeah.
Okay, so if I pick trials 1 and 2, is there a change in rate between 1 and 2? Does B have anything to do with that change in rate?
No.
Does A?
Yes.
Has everything to do with it, right? How did A change? And then rate?
Double.
So since they changed by the same factor, the exponent controlling them is a 1. All right, so 1. So I had a doubling here and I had a doubling here, so that makes it first order. So now which trials do we want to pick? 1 and 3? So nothing happens here, and here I have a doubling, and here I have a quadrupling. So the rate quadrupled, A had nothing to do with that quadrupling, B doubled, and that turned it into a quadruple. So for 2 to equal 4, 2's exponent needs to be a dose, a 2. So then I've got a 2 for the order for B. That's it. We good with that?